In this video, we'll be using elimination to attempt to solve a system of equations. This particular system has the two equations x plus 3y equals to 1 and negative 3x minus 3y equals to a negative 15. This particular system, again, we could use substitution by solving for one of the equations, but it just doesn't seem like a viable, smooth option. In this case, what I'm going to do is I'm going to look at these two equations and I'm going to do what is mathematically considered a phrasing inappropriately, but I'm going to add the two equations together. The more appropriate way to phrase this would be I'm adding both the left side of both equations and I'm getting something, and then I'm going to add the right side of both equations and get something. The reason why this is more appropriate to say is because you don't add two equations together. That doesn't make any sense. But you can add, I know if I add this side to this side, it's the same as though I'm adding this side to this side. So that's what I'm going to do with this. I'm simply going to use elimination, and elimination is by adding these two equations together, hopefully one of the variables will cancel out. Now, I'm doing this without doing any steps beforehand. This is not the way elimination generally works out. Elimination is generally done by having to multiply one of the equations on both sides by a specific number or value. So the reason why I don't have to do anything with this one is because if I add the x with the negative 3x, I get negative 2x. But when I add these two variables together, they just cancel out. Again, positive 3y minus 3y, I get 0y. That being the case allows me to eliminate the variable, that's why it's called elimination, and then therefore solve for x. Don't forget that after you've gotten x, you still need to go back and get y. Again, the solution to a system is not an x value, it's not a y value, it's a coordinate point, it's x comma y. So I've got my x value of 7, I'm going to go ahead and plug that back into one of these two equations. Again, in my eyes, this one looks a little bit more complicated, so I'm going to plug it into the first one, giving me 7 plus 3y equals to 1. If I subtract 7 from both sides, that's going to give me 3y equals to a negative 6, and therefore I'm going to divide by 3. Now, conveniently in this video and the last video, we got nice numbers. This is not always the case. Again, in this case, my solution is 7 comma negative 2. Be warned that there is possibility of getting some ugly looking fractions. Or again, like the last video also showed, we got some kind of awkward non-solution case. Again, that's when something comes up that doesn't seem logical. Well, let's go ahead and look at the next example and see what happens if I have a different form or something that, again, doesn't have the matching numbers right off the bat. So I've got 5x minus 2y here equals to, and then 18. So this is my systems of equations. This time, again, this little bracket just telling me that I have two separate equations here. They're not one equation and one separate equation separately entirely. They are two equations together in the same system. Now, for me to solve this set, there's a couple of options that I have. Again, the idea is I want to be able to add two variables together, in this case the x's or the y's, such that either the x's cancel out or the y's cancel out. In this situation, it actually looks like it's easier to deal with the y, and the reason for that is because if I multiply the whole equation by a negative 2, that'll change this y to be a positive 2y, and when I add it to this, it'll just cancel out. The reason why I probably wouldn't want to use anything else is because I'd have to multiply either this whole thing by a fraction, or, and this example does come up from time to time, I'd have to multiply this top equation by 5 and this bottom equation by 2, having to change both equations. And I would rather avoid that if I can. So again, in this case, I can multiply the top by 5 and the bottom by 2, or I can just be lazy and multiply just the top, the entirety of the top function, by a negative 2. So I'm going to go ahead and do that. Negative 2 multiplied by negative 2x minus y equals to negative 2 multiplied by negative 9. This here is going to provide me with the equation of a positive 4x plus 2y equals to a positive 18. That's my first equation. Again, I'm going to draw an arrow to that to show that. And then I'm going to write the second equation just below it. And I'm going to add these two things together. This is going to give me 9x. These two things are going to cancel out, is equal to 36. So therefore, x is equal to a value of 4. And again, we're not done yet. We have to make sure we take this x value and plug it back into one of the two original equations and solve for y. So I'm going to take this back into the original first equation. Now, you could technically plug it into this one if you trust yourself that you did all the math right, but on the off chance that you didn't do the math right, this is probably where the mistake would occur, somewhere in here. So I'm going to plug it back into the original untouched equation. It's going to give me negative 2 times 4 minus my y value equals to a negative 9. It's going to give me a negative 8 minus y equals to negative 9. I'm going to add 8 to both sides. I'm going to get negative y equals to negative 1. In doing so, that means I'm going to have y equals to 1. So my solution end result is going to be 4, 1 as the solution. Again, we want to write it as a coordinate point because that's really what it is. So this is how to solve, again, using elimination, making sure that you understand that you have to multiply either one or both, in some circumstances, both equations by a number so that one of the variables, when adding the left sides of the equations and the right sides of the equations together, that the one of the variables will end up canceling out.